Okay, so good morning, everyone. Use yours. I have to use this for my questions.
What's your time? There's Wi-Fi here.
Okay, so we're beginning our tutorial in physics. That's tutorial sheet 4. We're doing tutorial sheet 4. That is under circular motion. So just invite your friends to come live so that we do this. It's PHY101. We're doing tutorial sheet 4. So just share the link as soon as possible. Then we get to begin. Okay, so let's go to tutorial sheet 4. Since the board is not very good, I won't be writing the questions. I won't be writing the full questions. I'll only be collecting the data from the questions. Then we get to solve it. So if we go to tutorial sheet 4, I'll read the question. Then we just follow through, collect the data, and solve the question. So question 1 on tutorial sheet 4 is a carousel is initially at rest at t is equal to 0. It is given an angular acceleration of alpha, which is equal to 0.06 rads per second squared, which increases its angular velocity for 8 seconds. Determine the following quantities. A, the angular velocity of the carousel. B, the linear velocity of the girl located 2.5 meters from the center of the carousel. C, the tangential or linear acceleration of the girl. Then D, the centripetal acceleration of the girl. E, the total linear acceleration of the girl. So we have to understand from this question. First, we know that this is just circular motion. Circular motion. So if this is circular motion, it can either be uniform or non-uniform circular motion. And by uniform circular motion, we mean it's a circular motion where the speed is constant. So if something is going in a circle and it has constant speed, that means the motion is uniform circular motion. So uniform circular motion. Constant speed. Then we have non-uniform circular motion, the non-uniform circular motion. And here, the speed is not constant. So, varying speed. So So now, when something is going in a circle, we expect it to have acceleration. So the difference is that in non-uniform circular motion, there will be acceleration both along the circle, and there will also be acceleration which is towards the circle, which we call the centripetal acceleration. And we write it as AC and sometimes AR, meaning the radial acceleration or centripetal acceleration. Now, this centripetal acceleration is due to the constant change in direction of the velocity. As something is going around a circle at each interval, the direction of the velocity changes. It's always tangent to the circle, always tangent to the circle. So this change of direction in velocity is the one which produces the acceleration, which is centripetal, as we understand that acceleration is just the change in velocity. So if velocity is constantly changing in direction, this is the result, which is the centripetal acceleration. And then if it's non-uniform circular motion, then we expect to have a constant acceleration because the speed is changing, and that is what we call the tangential acceleration, and we write it as AT. So we have tangential acceleration and centripetal acceleration. So AT is tangential acceleration, and AC is centripetal acceleration. So what we know is that from Newton's second law of motion, for acceleration to be present, then we expect that there has to be a force that causes that acceleration. Now, for the centripetal acceleration, then we mean there is a force that is always keeping this thing moving in a circle to produce the centripetal acceleration. And that force is what we call the centripetal force, Fc. So for something to keep going in a circle and having a centripetal acceleration, we need the centripetal force, which comes about due to the summation of all the forces acting on that particular object, and the resultant of it is what we call the centripetal force. So what I mean is, let's say, take for example, we have a ball attached to a string and you swing it. So if you're swinging a ball on a string, that means it will be in a circle. Do I have something I can use?
Okay, we can have this one. The screen is just so small. Can you imagine?
So for example, if this is my string and then I have to swing it, if I have to swing the string, then this is going in circular motion. So as it is going in circular motion, the head of this USB is exhibiting uniform circular motion. That's if I'm moving it with constant speed. If I'm moving it with constant speed, then that is uniform circular motion. And the force that is keeping it going here, we know that we have forces, that is mg. Let's say it's at this point, so we have mg downwards. Then from the code we have tension. If you are to resolve these forces into their components and just find the summation of them, according to Newton's second law, we say summation of forces, it can be in the x-axis or y-axis. This produces an acceleration. So this ma, when the acceleration is centripetal, is what we call the centripetal force. So actually, a centripetal force is not a force acting on an object, but the resultant of all the forces acting on an object. That's what we call the centripetal force. So when it comes to summing up forces, you don't get centripetal force as one of them and add it to your summation. So, centripetal force is just the result of all the forces that you have on the object. The summation of that is the centripetal force. Now, before we tackle question 1, you need to get this point that question 1 involves not only circular motion, but it also involves rotational motion, which are very related. What do we mean? Rotational motion involves something that is rotating about a fixed axis. An example of something that rotates, we can talk about a bicycle. a wheel in a bicycle is constantly rotating about an axis. So that is rotational motion. Yet every particle, if this is my wheel, so we know it is something like this, my bicycle wheel, it's something like this. So the wheel itself is going in rotational motion, but every particle of it is undergoing circular motion. So every particle of this wheel is undergoing circular motion, while the wheel itself as a whole is undergoing rotational motion. Now, this rotational motion sweeps up an angle theta at every point of movement. Let's say we take an arc of length L, and this is the radius R. This from point A to B sweeps an angle theta, and this is what we call the displacement. So from here, we are able to conclude that therefore the rotational velocity and rotational displacement and rotational acceleration are related to the linear acceleration, tangential acceleration, and the centripetal acceleration, of which you'll be able to understand the details better as you start further. But we are able to conclude that this, the L here is just equal to R multiplied by theta. So this L is actually the change in length around the arc, which we call displacement when we come to linear motion. So if this is displacement, then we are saying displacement for rotational motion is just theta. But if you want to find the linear motion, the linear displacement from the angular displacement, it's r multiplied by theta. And from there, we're saying then the velocity, which is linear, is also equal to r multiplied by omega. This omega here is just this is the angular velocity. So omega is the angular velocity. Then we also have the acceleration, A. Now this acceleration, remember I mentioned that we have two accelerations, which is the tangential acceleration and the centripetal acceleration. So if I'm talking about the tangential acceleration, this one will also be equal to r multiplied by alpha, where alpha is the angular acceleration. So the linear acceleration, angular acceleration, and velocity, they follow same patterns just as motion, translational motion, which is just in one dimension. Translational motion is very related to rotational motion, and these are the relations. So the same way we are able to work with the three equations of motion under kinematics, the same applies for this topic. We are able to find the same equations of motion for the angular acceleration, for the angular velocity, and for the angular displacement. So now let's go back to question 1. I hope we have a foundation from there. A carousel is initially at rest at t is equal to 0. And so if we don't know a carousel, it's just something like a merry-go-round. I'm sure all of us are more certain with a merry-go-round. We know what it is. So a carousel is initially at rest at t is equal to 0. It is given angular acceleration of alpha, which is equal to 0.060 rads per second squared, which increases its angular velocity for 8 seconds. Determine the following quantities. A, the angular velocity of the carousel. B, the linear velocity of the girl located 2.5 meters from the center of the carousel. And C, the tangential acceleration of the girl. Then D, the centripetal acceleration of the girl. E, the total linear acceleration of the girl. So let us try to put that problem on the board. Okay, so we're talking about a carousel, so I'll draw. This is my carousel and this is its center of axis. So if I assume that the girl is somewhere here, then this distance from the center to there, I'll call it my radius, because that's the radius of the circle that she's sweeping her motion in. So if this is the radius r, and this is where the girl is, and that is my center. Now the question part A is asking for the angular velocity. So in the same way, we know that linear velocity is equal to the change in displacement and over the change in time. We are going to find the angular velocity, but just remember that this time angular velocity is omega. So angular velocity omega from, I want you to relate the two equations. A is equal to V minus V naught over T. This is in linear motion. We have alpha is equal to omega 2 minus omega 1 divided by the change in time. These equations are related, it's just that this one is for linear and the other one is for angular. So since the question is talking about angular, I'm concentrating on this equation. So alpha is equal to omega 2 minus omega 1 over change in time. And the question is asking for the final velocity, so we are calling it omega 2 because this is the final. So this is what we are looking for, the omega 2. The angular velocity. So what we have to do is just make it the subject, then see what we have to do. So what data do we have? We know it's starting from rest. So since it's starting from rest, that is our data. Omega 1 is equal to 0. And change in time, because it moved for 8 seconds, will be equal to 8 seconds. Then we have the angular acceleration, which is given in the question. Also, it's 0.060 rads per second squared. And what else do we have? We are looking for omega 2, which we don't know. So that is our question, and that is the data that we have from the question. So the question is, what is omega 2? So we are coming here and making omega 2 the subject of the formula. So what are we going to get from here? Let us rewrite this equation, making omega the subject. Okay, so we'll say, what should I write? Making omega 2 the subject, we'll get omega 2 is equal to alpha change in t, then plus omega 1. So if that is the case, we have alpha change in t plus omega 1. We're just supposed to substitute these numbers and get our result. So from there, we know that alpha is 0.060 seconds. So I say omega 2 will just be equal to 0.060 rads per second squared. Then multiplied by change in t, which is 8 seconds. Then plus 0. So from here, plug in the numbers, you'll be able to get the answer. And I'm sure from your calculations, you punch in the calculator, omega 2 is just equal to 0.48 rads per second squared. Rads per second squared. And we have found our part A. Then the next part B is saying the linear velocity of the girl located 2.5 meters from the center of the carousel. So now, we already have the angular velocity, and we already established that the linear velocity has a very good relation with the angular velocity. So, since we have the angular velocity, we are saying the linear velocity, so this is B, linear velocity, which is V, is just equal to R multiplied by omega. So now, omega is what we've already found. So, we're going to say V is equal to 0.48 rads per second squared. And the radius from the question we've been told this thing is, what is the radius there? 2.5 meters. So our R is just 2.5. So this is multiplied by 2.5 meters. So when you multiply this, I'm sure you'll be able to get an answer, and the velocity will just be equal to 1.2 meters per second. This is 1.2 meters per second. So remember that rads is not a dimension. That's why you find that in your answer, you don't have the rads again. So we have 1.2 meters per second. Now we go to the next part of the question. Oh, sorry, it's not rads per second squared. It's just rads. We're finding omega, which is velocity. So the seconds here cancelled with 1 second there, we remain with seconds. So we only have rads per second there, we only have rads per second here, and we multiply it by 2.5, we get 1.2 meters per second. So the next thing is we have to calculate the tangential acceleration of the girl. So the tangential acceleration, which is always tangent to the motion 80, the tangential acceleration is just equal to the r, which is the radius, multiplied by alpha, which is the angular acceleration. So the angular acceleration is already there in the question. So since the angular acceleration is already there in the question, we are saying the tangential acceleration 80 is just equal to the radius, which is 2.5 meters, then multiplied by 0.48 rads per second. So from here, we are looking for the tangential acceleration. So we are using the angular acceleration, which is given from the question. I'm sure you still have the data from the question. It's 0.060 rads per second squared. So from here, when you multiply this, we are able to get the tangential acceleration, which is equal to 2.5 meters multiplied by that. The dimensions, you see, I already mentioned that the rads is not a dimension. Therefore, our answer will just be in meters by seconds squared. So our answer, if you punch in the calculator, there, you're getting a 0.58 meters per second squared. So take time to go through the numbers and just make sure that you are able to verify those numbers. Then we go to part C of the question. Oh, this was part C. We go to part D. D says the centripetal acceleration of the girl. So this time around now we're looking for the centripetal acceleration AC. Now, this centripetal acceleration is always directed towards the center of the circle, that is AC. And this centripetal acceleration, we know that the centripetal acceleration is always equal to V squared over R. Let me just clean the board. So the centripetal acceleration AC, which is always towards the center of the circle, would just be equal to v squared over r, which is the radius, and in this case we already have the radius. So if you want, you can just come here directly and plug in the velocity, the linear velocity that we had already found. Or you can, we also understand that this v, so you can say but v is just equal to omega r. So this implies that AC is just equal to omega r squared divided by r, which just gives us AC is equal to omega squared r. And with this now you can just plug in your numbers, the answer that we got for omega, which is the angular velocity, and multiply it by the radius, which is r. So you have AC is equal to, what did we find for omega? Is 0.48 rads per second. Then multiplied by 2.5 meters. Then from there you can get the centripetal acceleration. So if you get the centripetal acceleration, just punch in the numbers, because I think I'll take a lot of time if I start punching numbers with the calculator. So you just punch in the numbers and get your answer at this point. Then we go to the next question, which is D. We are on E now, the total linear acceleration of the girl. So the linear acceleration of the girl is, we have the tangential here, then we have the centripetal acceleration. The linear acceleration is just the resultant of these two vectors. So we have tangential and centripetal. Now the resultant of these are what we call linear acceleration. And the linear acceleration A is just equal to the vector A tangential plus vector C, which is tangential. And so I understand from your vectors that you are able to know that this linear acceleration would just be equal to the root of AT squared plus AC squared. So you get the answer for AC and AT, plug in there, find the root, that is that will be the linear acceleration, and this linear acceleration will just be equal to, when you punch in your numbers, I hope I did punch the numbers, and unfortunately I didn't. So you can just get the value for tangential acceleration. I'm sure we found it earlier. For tangential acceleration we have 0.15, so this would be equal to the root of 0.15 meters per second squared, so it would be squared like that. Then plus the centripetal acceleration, what you got from this point, plug it in there, then find your answer. So that would be your linear acceleration. Then we are done with question 1. So the next thing will be, we need to look at question 2. Question 2. A ball of mass M attached to a massless string of length r is being moved in a vertical circle as shown. Show that the minimum speed that the ball needs at the top of the circle in order for it not to leave the circle is given by root of RG. So let me just draw a sketch of that question. Okay, so I'll pause for a moment and just try to check your comments and see what you need to improve. Then I'll continue in the next 5 minutes.